TW and THW conductors are not suitable for direct burial applications. These conductors are typically designed for indoor wiring and lack the necessary protection against the environmental factors present in direct burial scenarios. The conditions encountered underground, such as moisture, varying temperatures, and the presence of chemicals in the soil, can degrade the insulation of TW and THW conductors over time, leading to potential electrical failures and safety hazards. For direct burial applications, it is essential to use conductors specifically rated and designed for this purpose. Conductors with ratings such as RHH, RHW, or use are suitable for direct burial. RHH conductors are heat-resistant rubber-insulated conductors that are typically used in dry locations. RHW conductors are rubber-insulated conductors that are heat and moisture-resistant and can be used in wet or dry locations. Use conductors are underground service entrance cables that are specifically designed for direct burial applications. These conductors have robust insulation that provides excellent protection against moisture, chemicals, and mechanical damage. When selecting conductors for direct burial, it is crucial to consider the specific environmental conditions of the installation site. Factors such as soil type, moisture levels, and temperature ranges can influence the choice of conductor. In areas with high moisture content or corrosive soils, it may be necessary to use conductors with additional protective layers or specialized insulation materials. It is also important to follow all applicable electrical codes and regulations when installing direct burial conductors. These codes provide specific requirements for conductor size, burial depth, and other installation practices to ensure electrical safety and prevent damage to the conductors. The National Electrical Code, or NEC, is a widely adopted standard in the United States that provides detailed guidelines for electrical installations. Consulting the NEC and other relevant standards can help ensure that the direct burial conductors are installed correctly and safely. When connecting direct burial conductors, it is essential to use connectors that are specifically designed for direct burial applications. These connectors are typically made of corrosion-resistant materials and provide a watertight seal to prevent moisture from entering the connection. Improperly installed connectors can lead to corrosion and electrical failures over time. In addition to selecting the appropriate conductors and connectors, it is also important to ensure that the burial depth is sufficient to protect the conductors from mechanical damage. The NEC specifies minimum burial depths for different types of conductors and applications. These depths are designed to prevent damage from digging, landscaping, or other activities that may occur in the area. When installing direct burial conductors, it is also important to provide adequate protection against physical damage. This can be achieved by using conduit or other protective measures in areas where the conductors may be exposed to mechanical stress or abrasion. Conduit can also provide additional protection against moisture and chemicals in the soil. It is also important to properly mark the location of the direct burial conductors to prevent accidental damage during future digging or excavation activities. This can be done by installing warning tape or markers above the conductors to indicate their presence. Regular inspections of direct burial conductors can help identify potential problems before they lead to electrical failures. These inspections should include checking for signs of damage, corrosion, or insulation degradation. Any problems that are identified should be addressed promptly to prevent further damage and ensure electrical safety. In summary, when selecting conductors for direct burial applications, it is essential to choose conductors that are specifically rated and designed for this purpose. Conductors with ratings such as RHH, RHW, or use are suitable for direct burial. It is also important to consider the specific environmental conditions of the installation site, follow all applicable electrical codes and regulations, and use connectors that are specifically designed for direct burial applications. By following these guidelines, it is possible to ensure that direct burial conductors are installed correctly and safely, providing reliable electrical service for many years to come. The selection of appropriate grounding conductors, like those connecting ground rods in a grounding grid, demands careful consideration of environmental factors and code compliance. TW and THW insulation types are generally unsuitable for direct burial due to their limited resistance to moisture and soil chemicals. The National Electrical Code, specifically Section 300.5, outlines requirements for underground installations. Table 300.5 details minimum cover requirements, which vary depending on voltage and installation location. Direct burial cables or conductors must meet specific standards to withstand the harsh underground environment. Conductors with RHH, RHW, or reuse insulation are generally preferred. RHH offers heat resistance, while RHW provides both heat and moisture resistance. Use, designed for underground service entrance, boasts robust protection. Conductor size selection for grounding grid adheres to NEC 250.66. This section dictates sizing based on the size of the largest ungrounded service entrance conductor or equivalent for parallel conductors. For instance, if the service entrance conductors are two 500 kc copper conductors in parallel, the grounding electrode conductor must be at least 1/0 copper. Ground rods need to be at least 8 feet long and a minimum diameter, usually 1/2 inch for copper or 5/8 inch for steel or iron, unless listed. Section 250.53G describes supplemental electrode requirements, particularly regarding resistance to earth. If a single ground rod doesn't achieve 25 ohms or less resistance to earth, a supplemental electrode is required. This often involves installing multiple ground rods spaced at least 6 feet apart. The bonding jumper connecting the ground rod should be sized per NEC 250.66. For a grounding grid, multiple ground rods are interconnected to create a low impedance path to earth. The conductors connecting these rods form the grounding grid. Typically, bare copper conductors are used, but insulated conductors approved for direct burial, like RHW or use, are also acceptable. When connecting grounding conductors to ground rods, exothermic welding, compression connectors listed for direct burial, or reversible crimp connectors are preferred. These methods ensure a permanent, low-resistance connection. Mechanical connections, if used, must be accessible for inspection unless listed for direct burial. Underground installations require specific burial depths to protect conductors from physical damage. NEC Table 300.5 outlines minimum cover requirements based on voltage and location. For example, direct burial cables rated 600 volts or less typically require a minimum cover of 24 inches. Rigid metal conduit or intermediate metal conduit reduces the required cover depth to 6 inches in some cases. Proper backfilling practices are crucial to prevent conductor damage. Avoid sharp rocks or debris that could puncture the insulation. Use clean backfill material, such as sand or fine gravel, to surround the conductors. The grounding electrode system should be tested periodically to verify its effectiveness. Fall of potential testing measures the resistance to earth. If resistance exceeds 25 ohms, additional ground rods or other measures are necessary to improve grounding. Soil composition significantly affects grounding system performance. Sandy soil has higher resistance than clay soil. Soil resistivity testing helps determine the optimal location and configuration for ground rods. In corrosive soil environments, special precautions are necessary. Encapsulating ground rods in concrete or using corrosion-resistant electrodes extends their lifespan. The NEC mandates that all metal underground water pipes used as grounding electrodes must be supplemented by an additional electrode, such as a ground rod or ground ring. This ensures redundancy in the grounding system. Ground rings, encircling a building or structure, provide a low-impedance ground path. They must be buried at least 30 inches deep and consist of bare copper conductor at least 2/0 in size. Concrete encased electrodes, also known as UFA grounds, involve encasing a bare copper conductor at least 20 feet long within a concrete foundation. This provides a highly effective grounding electrode. When multiple buildings or structures are supplied from a common service, a grounding electrode system must be established at each building or structure. These grounding systems are interconnected to ensure equipotential bonding. The equipment grounding conductor runs with the circuit conductors to provide a low impedance path for fault current. This conductor connects non-current carrying metal parts of electrical equipment to the grounding electrode system. Proper grounding and bonding are essential for electrical safety. They minimize the risk of electric shock and equipment damage. Regularly inspect and test grounding systems to ensure continued effectiveness. Always follow the NEC and other applicable standards when designing and installing grounding systems. Local codes and regulations may impose additional requirements. The use of TW or THW conductors for direct burial in a grounding grid is not recommended due to their limited resistance to moisture and soil chemicals. Conductors with RHH, RHW, or use insulation are more suitable. Proper installation practices, including appropriate burial depth, backfilling, and connection methods, are critical for ensuring the long-term performance and reliability of the grounding system. Regular testing and maintenance are also necessary to identify and address any potential problems. In addition to the NEC requirements, local codes and regulations may impose additional requirements for grounding systems. It is important to consult with local authorities to ensure compliance with all applicable standards. The design and installation of grounding systems should be performed by qualified electricians or engineers with experience in grounding and bonding. Proper grounding and bonding are essential for electrical safety and can help prevent electric shock and equipment damage. Therefore, it is crucial to follow all applicable codes and regulations and to use qualified personnel for the design and installation of grounding systems. Furthermore, the size of the grounding conductor must be sufficient to handle the available fault current. NEC Table 250.122 provides guidelines for sizing equipment grounding conductors based on the rating of the overcurrent protective device. In some cases, it may be necessary to use a larger grounding conductor than required by the table to ensure adequate fault current carrying capacity. The grounding electrode conductor should be connected to the grounding electrode system using a listed connector or by exothermic welding. The connection must be accessible for inspection and testing. When using multiple grounding electrodes, they should be bonded together to form a grounding electrode system. This ensures that all grounding electrodes are at the same potential. The bonding jumpers connecting the grounding electrodes should be sized according to NEC 250.66. The grounding electrode system should be located as close as practicable to the service entrance. This minimizes the length of the grounding electrode conductor and reduces impedance. The grounding electrode system should be protected from physical damage. This can be achieved by installing the grounding electrodes in a protected location or by using a protective enclosure. Regular inspections and testing of the grounding system are essential to ensure its continued effectiveness. The grounding system should be tested at least annually to verify that it meets the requirements of the NEC and other applicable standards. Any problems that are identified should be addressed promptly to prevent electrical hazards. In addition to the requirements of the NEC, other standards and guidelines may be applicable to grounding systems. These include IEE standards for grounding and bonding, as well as manufacturers' recommendations for specific equipment. It is important to consult with these standards and guidelines to ensure that the grounding system is properly designed and installed. The design and installation of grounding systems can be complex and require specialized knowledge and experience. It is important to use qualified electricians or engineers for this work. Proper grounding is essential for electrical safety and can help prevent electric shock and equipment damage. Therefore, it is crucial to follow all applicable codes and regulations and to use qualified personnel for the design and installation of grounding systems. Finally, remember that even though RHH, RHW, and use are suitable for direct burial, verify the specific voltage and temperature ratings match your requirements. The information provided here is for guidance only and does not constitute professional engineering advice. Always consult with a qualified electrical engineer or electrician for specific design and installation recommendations. When installing ground rods, ensure they are driven deep enough to reach permanent moisture. This depth varies depending on local climate and soil conditions. Check local codes for specific requirements. Spacing ground rods adequately minimizes overlapping zones of influence, improving grounding effectiveness. The minimum spacing should be at least equal to the rod length. Consider using ground-enhancing compounds in areas with poor soil conductivity. These compounds improve the contact between the ground rod and the surrounding soil. Document the location and configuration of the grounding system for future reference. This information is valuable for maintenance and troubleshooting. When working on electrical systems, always to energize the circuit before making any connections or modifications. Use appropriate personal protective equipment, such as gloves and safety glasses. Be aware of underground utilities before digging. Contact local utility companies to locate any buried lines. Follow lockout/tagout procedures to prevent accidental re-energization of the circuit. If you are not qualified to perform electrical work, hire a licensed electrician. Improper electrical work can be dangerous and can lead to serious injury or death. Always prioritize safety when working with electricity. The grounding system is a critical component of electrical safety. Ensure it is properly designed, installed, and maintained.